all volumes in reinforced concrete need a minimum reinforcement. In part 1, we will learn about the code requirements and the calculation methods as they are stated in the Eurocodes. In part 2, specific examples are worked out, and finally an overall conclusion is given in part 3. In part 1, code requirements and calculation methods, we will start with a general approach to minimum reinforcement, followed by the minimum reinforcement to avoid brittle failure. We will continue in the following parts with minimum reinforcement needed for crack control, with or without specific crack width specifications, and restricted deformation using Graph's formulas or total free strain. Part 1 will be concluded by a summary of the 8 different methods. The code requirements for minimum reinforcement is not restricted to one article in the codes. It is smeared out over Chapter 7 and 9 of Eurocode 2 Part 1.1 and in the annexes of Eurocode 2 Part 3. Minimum areas of reinforcement are given in order to prevent a brittle failure, wide cracks, and also to resist forces arising from restraint actions. Reinforcement due to restraint deformation is clearly regarded here as a minimum reinforcement and should therefore not be accumulated with reinforcement coming from external actions. However, reinforcement needed for overall temperature increase or decrease after the construction is built must be combined with other load cases. Plainly or lightly reinforced concrete members. These are structural concrete members having no reinforcement or less reinforcement than the minimum reinforcement. This means that if in a concrete member you do not put the minimum reinforcement as required, then it should be regarded this member as plain concrete. In the calculation of stresses and deflections, cross-sections should be assumed to be uncracked provided that the flexural tensile stress does not exceed FCTF. The value of FCTF may be taken as FCTM or FCTM flexural, provided that the calculation for minimum tension reinforcements is also based on the same value. The flexural tensile stress is given by this formula here. It means that only for elements with a depth higher than 600 millimeters, it is more economical to calculate the minimum needed reinforcement with the flexural tensile strength instead of the mean tensile strength. If you use 0.7 FCTM instead of FCTM for the value of FCT effective, then the cracking moment should also be calculated with 0.7 FCTM. And this will have an influence on the total deflection of the element. Of course, there are some general rules for minimum reinforcement. Like for instance, for slabs, the transverse reinforcement should be at least 1/2 of the main reinforcement, or in absence of brittle failure, the minimum reinforcement must be bigger than 1.2 times the required reinforcements. There is also a formula for minimum reinforcement for columns, and for walls there is a minimum reinforcement or minimum reinforcement requirement of 0.1% per direction per face. In the general rules that is stated in this presentation, those methods of slabs, columns and walls, those technological requirements of minimum reinforcement are not included. The minimum reinforcement due to brittle failure is given by the following formula. The number in the right top represents the method number. The formula can easily be understood by a simplified calculation, assuming a beam subjected to a bending moment, causing a tension of FCTM in the concrete. The lever arm is taken as 0.9 times the effective depth of the section. The effective depth of the section is assumed to be 0.9 of the total height of the section. If you substitute this in those simplified formulas, you arrive at the formula which is stated here. A lower bound of the minimum reinforcement due to brittle failure is found by assuming a tensile stress of 2.5 megapascal, that corresponds with a concrete C2530, and a steel stress of 500 megapascal. For members pre-stressed with permanently unbounded tendons or with external pre-stressing cables, it should be verified that the ultimate bending capacity is larger than the flexural cracking moment. A capacity of 1.15 times the cracking moment is sufficient. But there's another rule stating that in pre-stressed members, no minimum reinforcement is required in sections where under the characteristic combination of loads and the characteristic value of pre-stress, the concrete is compressed or the absolute value of the tensile stress in the concrete is below FCT effective. Ultimate bending capacity must be 15% larger than flexural cracking moment, and this is in ULS. If in SLS the concrete stress stays below FCT effective, no minimum reinforcement is needed. This way, there is no contradiction between those two elements. You can regard the first part as brittle failure and the second part as crack control. All 8 methods that we will see will be based on a simply supported beam with a rectangular cross-section. This cross-section will be 600 millimeters. Will have a depth of 600 millimeters and a width of 300. It will be used with a normal concrete grade and a normal steel grade. And it will have a concrete cover of 50 millimeters, a creep coefficient of 2. And we will use, just for comparison in the whole exercise, a bar diameter of 12 millimeters. If we take now the method 1 for brittle failure, then we only have to check those two formulas. It's quite straightforward. If you fill it in, you obtain the maximum of the two, which is 241 millimeters.